Hello, and welcome to VideoTec. The subject of this month's program is the sequential multi-point fuel injection system used on 1991 Jeep Cherokees, Comanche, and Wrangler models equipped with 2.5 and 4-liter engines. This is the brain of the new fuel injection system, a microprocessor-controlled device called the SPEC2, which stands for Single Board Engine Controller. The SPEC2, or engine controller as we'll be referring to it for the rest of this program, is new for 1991. It replaces the ECU, or electronic control unit, used on previous year's models. The engine controller is a digital computer that can adapt its programming to meet changing operating conditions. It regulates ignition timing, air-fuel ratio, emission control devices, charging system, speed control, and idle speed. The engine controller receives information on existing engine conditions in a form of electrical input signals from various switches and sensors. Based on these inputs and its own internal programming, the engine controller regulates various engine and vehicle operations through different system components known as engine controller outputs. The engine controller manages fuel injection in basically the same manner as the Renix sequential MPI system did. However, there are many changes on this 1991 system. Like the Renix ECU, the engine controller fires the injectors in a specific sequence and maintains the optimum fuel-air ratio of 14.7 parts of air to 1 part of fuel by constantly adjusting injector pulse width. MPI injectors are electronically activated solenoid assemblies. When energized, these solenoids pull the fuel metering plunger from its seat, allowing pressurized fuel to spray through the opening into the intake manifold. Injector pulse width is simply the length of time the injector is held open. A wide pulse width means the injector is open for a long time, producing a rich mixture, while a narrow pulse width means the injector is open for a short time, producing a lean mixture. The engine controller adjusts injector pulse width based on voltage signals it receives from the various input sensors and switches, and regulates engine and vehicle operations through different outputs. Now that we've reviewed the basic operation of the system, it's a good time to review the many changes and improvements that have been made for 91. As I've already mentioned, the engine controller now controls the charging system, speed control, and the security alarm module. The engine controller also stores fault messages, a new feature on Jeep vehicles. There are 2 ways to access the stored faults, one of which uses the DRB2. There's also a new 1991 cartridge for the DRB2. The new cartridge works hand in hand with the new layout for the diagnostic manuals. The new DRB2 screens feature 2-line fault messages, which are more descriptive than in previous years. What's more, the 91 cartridge is universal and can be used on all Chrysler vehicles. The engine controller is not the only new component in the SPEC2 system. In fact, the only sensor that has not changed is the MAP sensor, which is the same as that used on previous models. This means the voltage values that apply to last year's sensors are no longer applicable. That's important to remember when performing diagnostics. When we come back, we'll review the new inputs and outputs. There are some new engine controller inputs on 1991 Jeep models, while some inputs and outputs on previous year's models have been dropped, including the knock sensor, the latch relay, the oxygen sensor heater relay, the EGR valve solenoid, and the ignition control module. The 1991 inputs are air density received from the MAP, or manifold absolute pressure sensor, engine RPM, speed received from the crankshaft position sensor, battery voltage, alternator field sense, sync signal, manifold air temperature or MAT sensor, engine coolant temperature sensor, throttle position sensor, oxygen sensor, distance or speed sensor, speed control switches, ignition circuit sense, AC Request Predict, the Instrument Panel AC Select Switch, Park Neutral Safety Switch, Power Steering Pressure Switch, Brake Switch, and the SCI Receive. Some sensor inputs are absolutely necessary for the vehicle to run at all. For example, if there is a loss of signal from the MAP sensor, the MAT sensor, the coolant temperature sensor, the oxygen sensor, the throttle position sensor, or any combination of those sensors, the engine controller will keep the vehicle running by entering a limp-in mode, substituting a value for the lost sensor or circuit. Our first input is one of the most important. It's the manifold absolute pressure, or MAP sensor, mounted here. The MAP sensor is connected to the engine controller electrically and to the throttle body by a vacuum hose. This sensor measures manifold absolute pressure and ambient pressure when the ignition is first turned on, during cranking, and at wide open throttle. It provides a 0 to 5 volt signal, which allows the engine controller to calibrate the amount of fuel supplied to the engine. The MAP sensor is the only input sensor that is not new for 91. Probably the next most important input is the crankshaft position sensor, or CPS. The new CPS works on a different principle than last year's sensor. Mounted here on the transmission bell housing, the CPS detects engine speed and crankshaft position using a Hall effect speed sensor. When a flywheel notch passes the sensor's magnet, the magnetic field begins to shift. The field then snaps back to its original position when the metal between the notches is aligned with the sensor, inducing a voltage in the sensor's pickup coil. These voltages allow the engine controller to actually count the passing notches. The signal generated provides engine speed and crankshaft position information to the engine controller, which uses this information to determine proper fuel injection and ignition timing. The CPS is a vital input to the engine controller. Without the CPS signal, a no-start condition will result. Battery voltage signal is another important input. The engine controller needs to know battery voltage level to regulate the alternator field cycle and alter fuel injector pulse width according to available voltage. If the battery voltage drops, the engine controller will increase the amount of time the injector is on to compensate for the reduced fuel flow caused by the lowered voltage. The result is that the same amount of fuel is delivered to the engine. An input that's closely related to battery sense is the alternator input. The engine controller's basic voltage regulating job is to keep the charging system voltage between 13.4 and 15 volts. The alternator input informs the engine controller what voltage level is supplied to the ignition coil and fuel injectors. The engine controller then adjusts fuel injector pulse width and alternator field based on this input. Our next input, the sync signal generator, is located here in the distributor. Like the crankshaft position sensor, the sync signal generator is a Hall effect sensor. The sync signal works in conjunction with the crankshaft position sensor to provide the engine controller with inputs to establish and maintain correct injector firing order. In short, these two sensors work together to tell the engine controller where the pistons are and at what stage of the running cycle they are, so that the injectors can deliver fuel to the right cylinder at precisely the right time in the cycle. Without a sync signal, a no-start condition will result. As the pulse ring rotates in the distributor, it passes through a magnetic field. When the pulse ring enters the signal generator, the magnetic field becomes weaker, indicating the position of piston number 3 on the 6-cylinder engine and piston number 4 on the 4-cylinder engine. When the ring leaves the signal generator, the magnetic field becomes stronger, indicating the position of piston number 4 on the 6-cylinder engine and piston number 1 on the 4-cylinder engine. The engine controller receives this information and is able to determine the proper order of injection sequence. Our next two inputs are the manifold air temperature, or MAT sensor, and the coolant temperature sensor. The manifold air temperature sensor measures the temperature of the air entering the intake manifold. It then sends an analog voltage signal to the engine controller, allowing it to compensate for changes in the air density due to temperature. The coolant temperature sensor sends an analog signal to the engine controller, which is used to calculate injector pulse width based on engine temperature. Input from this sensor will also affect idle speed motor position and spark advance operation. Both of these sensors are thermistors, in which the sensor resistance decreases as temperature increases. Let's take a look now at where these two sensors are located. The manifold air temperature sensor is located in the intake manifold, where it measures the temperature of the air entering the intake manifold. On the 2.5-liter engine, the MAT sensor is located here, next to the idle speed motor. On the 4-liter engine, the MAT sensor is located here. On both the 2.5 and the 4-liter engines, the coolant sensor is located here, in the thermostat housing. The throttle position sensor, or TPS, is mounted on the throttle body. It contains a potentiometer operated by opening and closing the throttle plate. As the position of the throttle plate changes, the resistance of the TPS changes. The engine controller supplies approximately 5 volts to the TPS through terminal C. The output voltage sent from the TPS to the engine controller represents the throttle plate position. The input signal voltage from the TPS varies from approximately 1 volt at idle, with the throttle plate at its minimum opening, to 4 volts at wide open throttle. Along with inputs from other sensors, the engine controller uses the TPS input to determine current engine operating conditions and adjust fuel injector pulse width and ignition timing. Also, on automatic transmission equipped vehicles, the TPS signal is split and is used for both the fuel system and automatic transmission computers. Note that in all cases, the throttle position sensor is not adjustable. In addition to sensors, the system also has a number of relays which provide various inputs to the engine controller. You'll find many of these relays in the Power Distribution Center, located here on Cherokee and Comanche models, and here on Wrangler models. One of these relays, the one for the starter, provides our next input. The engine crank signal from the starter relay provides a signal to the engine controller to indicate when the engine starter is engaged. When the engine controller determines that the starter is engaged, it starts looking at the inputs from the crankshaft position sensor and the sync signal generator. If the engine controller does not receive a CPS signal within 3 seconds of cranking the engine, it will shut down the fuel injection system. Another input is the exhaust gas oxygen sensor, or the O2 sensor as it's commonly known. The same sensor is used for both the 2.5 and the 4-liter engines. The oxygen sensor is mounted in the exhaust downpipe and provides an input voltage to the engine controller. The sensor detects exhaust oxygen content from a chemical reaction within the sensor. Unlike previous O2 sensors, the O2 sensor on 1991 fuel injection systems is not just a variable resistor, it produces a voltage signal. When the mixture is rich, the exhaust gas will have a low oxygen content, and the voltage signal will be approximately 1 volt. When the mixture is lean, the exhaust gas will have a high oxygen content, and the voltage signal will be low, approximately 0.1 volt. The engine controller uses this information to fine-tune the air-fuel ratio by adjusting injector pulse width. The oxygen sensor also contains a ceramic resistance type heating element that runs on 12 volts supplied by the fuel pump relay in the Power Distribution Center. For 1991, the heating element is on at all times and is no longer controlled by its own relay. The heating element maintains the sensor at its proper operating temperature, allowing the system to enter into closed-loop operation sooner. Obviously, because of its job, The oxygen sensor is vital to both engine performance and emissions. If you suspect a problem in the oxygen sensor, you'll need to troubleshoot it with the DRB2 and the powertrain diagnostic manual. Another input that's new for 1991 is the vehicle speed or distance sensor. The engine controller uses the distance sensor to detect if the vehicle is moving and at what speed it's moving. You'll find the distance sensor mounted in the transmission extension housing on two-wheel drive vehicles and in the transfer case extension housing on four-wheel drive vehicles. The distance sensor generates 8 pulses per shaft revolution. By comparing the number of pulses to the time elapsed, the engine controller can determine vehicle speed and distance traveled. In addition to distance or speed, the sensor is used for idle speed control and works in conjunction with the throttle position sensor to detect decel conditions. The distance sensor is also used as a reference for the emission maintenance reminder light and works with our next input, the speed control system.
The speed control switches supply 3 separate inputs to the engine controller. They are on-off, which informs the engine controller that the speed control system has been enabled; set, which informs the engine controller that a set speed has been selected; and resume, which informs the engine controller that the previous set speed has been selected. Resume also has a tap-up feature. Well, we've looked at a lot of inputs so far. This next input, the ignition sense circuit, is the one that gets the system and all its inputs up and running. When the ignition key is turned to the on position, the engine controller receives a signal that the ignition circuit has been activated. The engine controller will then start looking at the other input signals. Our last series of inputs all inform the engine controller of sudden loads on the engine, so that the controller can compensate by adjusting fuel injector pulse width and ignition timing. Let's start by looking at 2 closely related inputs: the instrument panel air conditioning select switch and the air conditioning request signal. When the driver positions the mode lever in the air conditioning position, the engine controller receives an AC select signal. It also receives a request signal from the air conditioning temperature control thermostat. Listen to the engine RPM when I select the air conditioning mode again. What you heard was the click of the AC clutch engaging, and then the engine controller increasing idle speed using the idle speed motor. The system prevents idle speed undershooting and overshooting due to the changing load on the engine caused by the AC compressor. It's also important to note that whenever the AC clutch is energized, the engine controller also energizes the radiator fan relay. This occurs regardless of engine coolant temperature. Now, we'll start the engine again and look at some more inputs that cause the engine controller to increase idle speed in order to avoid stalling under increased load. On vehicles with automatic transmissions, a gear indicator signal is sent to the engine controller when the gear selector lever is moved to a drive range. This signal comes from the park neutral switch and allows for idle speed compensation by the engine controller. Manual transmissions do not provide a gear indicator signal to the engine controller. Well, we've got the engine running at idle and the transmission in drive with the vehicle stationary. It's under conditions such as these that our next input, the power steering pressure switch, comes into play. Cherokee, Comanche, and Wrangler vehicles equipped with power steering with a 2.5-liter engine all utilize a power steering pressure switch. When power steering pressure exceeds a predetermined level, such as during parking maneuvers when power steering pump pressures are high, the power steering pressure switch sends a signal to the engine controller, which then raises idle speed through the idle speed motor to prevent the engine stalling under the increased load. Another input is the brake switch. The engine controller uses this input to determine if the brakes are on or not. The brake switch is mounted on the steering column support under the instrument panel. Now, when the brakes are applied, if the engine controller sees minimum TPS, a lower speed sensor rate, and the brake switch on, it recognizes a decel condition and opens up the idle speed motor. The brake switch will also disengage the speed control if it was engaged. On vehicles equipped with automatic transmissions such as this Cherokee, the brake switch signal is also used as an input to the transmission controller.
The last input we'll look at is very important when a fault appears in the system that needs to be diagnosed using the DRB2. This is where the vehicle diagnostic connector is located on Cherokee and Comanche models. When the DRB2 is connected here, the DRB2 can receive data from the engine controller through the When we return, we'll be taking you through the outputs. There are a wide variety of engine controller outputs. The ASD, or automatic shutdown relay, fuel injectors, fuel pump relay, ballast resistor, ballast bypass relay, ignition coil, automatic idle speed motor, upshift lamp, tachometer, check engine lamp, EMR, or emission maintenance reminder lamp, SCI transmit, shift indicator lamp, alternator lamp, and vehicle theft alarm. Our first output is new for 1991. It's the auto shutdown relay located in the power distribution center. The ASD relay is used by the engine controller to supply voltage to the injectors, ignition coil, and the alternator. The engine controller regulates ASD operation by switching the ground circuit off and on. The engine controller will only ground the relay when the ignition switch is in the run or crank position, and some activity is sensed through the crankshaft position sensor and the sync pulse signal in the distributor. If the engine controller senses the RPM signal has stopped, it will remove the ground from the relay coil, which will remove power from the circuit. Fuel injectors are the next output we'll look at. Jeep models use a sequential multi-point fuel injection system. This means there is an individually controlled fuel injector for each cylinder. The injectors are attached to a fuel rail containing a pressurized fuel supply. The nozzle ends of the injectors are positioned into openings in the intake manifold just above the valve ports of the cylinder head. Because each injector is connected to 12 volts, the injector is energized when connected to ground through the engine controller. The injector uses electromagnetism and spring pressure to open and close the fuel metering plunger. When connected to battery voltage, the coil of wire in the injector becomes an electromagnet. The magnetic field pulls the plunger off its seat against spring pressure, spraying a fine mist of fuel above the intake valve. As mentioned at the beginning of this program, the length of time the plunger is open is called pulse width. The longer the pulse width, the richer the mixture, and the shorter the pulse width, the leaner the mixture. On Cherokee, Comanche, and Wrangler models, the fuel pump relay, our next output, is located in the power distribution center. The engine controller energizes the fuel pump through the fuel pump relay. Battery voltage is applied to the relay from the ignition switch. The relay is energized when a ground is provided by the engine controller. Cherokee and Comanche models have a ballast resistor located in line between the relay and the fuel pump. The ballast resistor's function is to reduce fuel pump speed and noise when the ignition key is in the on position. Most of the time when the fuel pump is energized, voltage is supplied to the fuel pump through the ballast resistor. During engine cranking and wide open throttle, the ballast resistor is bypassed and the fuel pump receives its voltage from the ballast bypass relay. The increased voltage speeds up the fuel pump to compensate for higher fuel demand. On Cherokee and Comanche models, the ballast bypass relay is mounted on a bracket next to the power distribution center. Note that Wrangler models do not use a ballast resistor or a ballast bypass relay in the fuel pump circuit. The engine controller operates the fuel pump through the fuel pump relay during all operating conditions. Our next output is the ignition coil. It's located on a bracket next to the distributor. The engine controller receives inputs from the various sensors, and based on this information, it determines the proper ignition timing and provides the coil with a ground signal to trigger the secondary voltage of the ignition coil. Base ignition timing is not adjustable. The engine controller adjusts ignition timing to meet changing engine operating conditions. The idle speed motor is mounted on the throttle body. It is used by the engine controller to control engine idle speed. The throttle body has an air bypass passage that provides air for the engine at idle when the throttle plate is closed. The idle speed motor pintle protrudes into the air bypass passage and regulates airflow through it. Based on various sensor inputs, the engine controller adjusts engine idle speed by moving the pintle in and out of the bypass passage. When the engine is cold, the engine controller increases idle speed by retracting the pintle, allowing more air into the engine, and by injecting more fuel. As the engine warms up, the engine controller extends the motor pintle into the air passage to reduce the amount of airflow. The idle speed stepper motor can be tested using the DRB2 or Miller tool number 7558. Our next series of outputs can all be found in the vehicle instrument cluster. Vehicles equipped with a manual transmission will have an upshift lamp located in the instrument cluster. The lamp is controlled by the engine controller and lights up to tell the driver when to shift to the next highest gear for the best fuel economy. The engine controller will turn the lamp off after 3 to 5 seconds whether or not the driver shifts. Some vehicles are equipped with a tachometer. Once again, the engine controller supplies the tachometer with the engine RPM signal. The check engine lamp has several functions. It alerts the driver if the engine controller has recorded a hard fault related to emission or sensor signal. It also lights up if a sensor fails or goes out of range and the vehicle enters a limp-in mode. It can also be used to retrieve fault codes. By cycling the ignition switch on, off, on within 5 seconds, the engine controller will display any stored fault codes in a series of flashes representing numbers. An exact description of the fault condition can then be obtained by looking up the fault code in the service manual or student reference guide. The emission maintenance reminder lamp informs the driver that components of the vehicle's emission system are scheduled for replacement or service. The EMR function is built into the engine controller. The engine controller reads the distance sensor and stores the mileage information in a non-volatile but resettable memory. When the engine controller sees that the appropriate mileage has been accumulated, it will turn on the EMR lamp. The lamp must be turned off and the engine controller reset by using the DRB2 diagnostic tester. Also, if the engine controller was replaced, the mileage recorded on the odometer must be entered into the new engine controller using the DRB2. Vehicles equipped with the base cluster feature another output on the instrument panel, the alternator lamp. The alternator lamp will light up if the engine senses a low charging condition, such as all accessories turned on with the engine at idle. Once the engine controller compensates for the increased accessory electrical load by raising the idle speed, the lamp will go out. Another output, the CCD vehicle theft alarm, is found only on the 4-liter Cherokee. On Cherokee models equipped with this option, the security alarm module sends a signal to the engine controller to enable it to start the engine. If the security alarm is activated, no signal through the CCD bus will be seen by the engine controller, and therefore the engine will not start. The engine controller will not allow spark or fuel delivery to the fuel injection system. If the engine controller is replaced in the vehicle, the security system becomes operable only after 20 engine starts. This design feature is intended to prevent problems with the security alarm in the assembly plant. If you install a new engine controller in a customer's car, be sure to start the engine 20 times so that the alarm system is operable. A functional engine controller that has been used in a vehicle equipped with the vehicle theft security system cannot be used in another vehicle that is not equipped with the security alarm module. That brings us to our last output, the SCI transmit, which is the serial data communication transmit circuit for the DRB2. This connector is where the DRB2 plugs into the SCI transmit circuit. We've already talked about its function as an input. In the output mode, the engine controller transmits data to the DRB2 through the SCI transmit circuit. Well, we've covered a lot of material in this program, so before we end, let's take a moment to review the many inputs and outputs that make up the engine control system. The inputs are air density received from the MAP, or manifold absolute pressure sensor, engine RPM, speed received from the crankshaft position sensor, battery voltage, alternator field sense, sync signal, manifold air temperature sensor, engine coolant temperature sensor, throttle position sensor, ignition circuit sense, oxygen sensor, vehicle distance or speed sensor, speed control switches, AC request predict, the instrument panel AC select switch, park neutral safety switch, power steering's pressure switch, brake switch, and the SCI receive. The outputs are fuel injectors, fuel pump relay, automatic idle speed motor, the ASD or automatic shutdown relay, alternator field, ballast bypass relay, check engine lamp, EMR or emission maintenance reminder lamp, ignition coil, radiator fan relay, SCI transmit, shift indicator lamp, speed control vacuum solenoid, speed control vent solenoid, tachometer on vehicles so equipped, alternator lamp, and the vehicle theft alarm. Well, that about wraps up this VideoTec on the theory of operation behind the 1991 Jeep 2.5 and 4-liter Jeep sequential fuel injection systems. In next month's program, our technician will show you how to troubleshoot the system using the powertrain diagnostic manual and the DRB2 with the new 1991 cartridge. See you next month.